Welcome back. In today's video, we want to find the voltage across the capacitor and the inductor. Here we see that we have a sine for a current source. As we mentioned in the study of sinusoidal analysis, we always adopt the cosine reference with a positive amplitude. So first we want to convert the current source into a cosine with a positive amplitude, and then transform the circuit into the phasor domain. So we can achieve that. So I of t is equal to 35 times cosine of omega t minus 110 degrees. Omega is 300. We achieve that by using the trig identity. Cosine of x is equal to plus or minus sine of x plus or minus 90 degrees. We can then write this as 35 with an angle of minus 110 degrees. And this is in amps. The relationship that allows us to move from time to phasor domain is that a signal x of t that is equal to a times cosine of omega t plus theta can be transformed into the phasor domain, and whenever that transforms to the phasor domain, the phasor counterpart of x of t is equal to a times the complex exponential e to the j theta, which is also equal to a with an angle of theta. We can then go ahead and transform our impedances. The impedance of the resistor stay the same in the phasor and time domain. However, the impedances of the capacitors and inductor is transformed. So the impedance for our capacitor is equal to 1 divided by j omega c, which is equal to minus j 16.67 with a unit of ohms. The impedance for the inductor is equal to j omega L, which is equal to j times 4.5 ohms. We can now choose the method of analysis. In this case, let's use the voltage division. Let's use voltage division and node voltage method. So let's start with node voltage. Or let's change that and start with voltage division. To use voltage division, we can start by using source transformation to transform our current source into a voltage source, which will be in series with a resistor Rs. And then we can combine our impedances and then find the voltage across that by using voltage division. So after we transform our source, we then get a source Vs in series with our resistor Rs, which is equal to our resistor R. And we have an equivalent impedance, and let's call that Z capital EQ. So we transform our source by saying that Vs is equal to Is times R, which is equal to 35 with an angle of minus 105. Excuse me. Earlier we had said 110, which we should have said 105. So we go back to our source transformation, which we times our current IS times our resistance of 80 ohms, and our current is in milliamps. So then we have to change that back to milliamps, and then we can include our milli, which we then get a voltage of 2.8 with an angle of -105, and that's in volts. So Z equivalent in this case, capital EQ, is the combination of our capacitor and inductor. So 1 over j omega c plus j omega L is equal to minus j 12.17, and that's in ohms. So we can now apply voltage division. The reason for going into or transforming the circuit into a series circuit, the single loop in effect divides the source voltage among a series of resistor, in this case impedances. So by combining the two impedance that we want the voltage across, the source voltage then divides through by the impedances. So by using voltage division, the voltage across the capacitor and inductor, in this case, the voltage across Z, capital EQ, is equal to the targeted impedance, so the impedance that we want the voltage across, which is ZEQ, and that is minus J 12.17 divided by the total impedance of the circuit, so the equivalence impedance of the circuit. So there's Z common EQ, which is going to be the resistance, the impedance of the resistor, 80 ohms, plus the impedance ZQ. So it's going to be 80 minus J 12.17, and we multiply that by our voltage, Vs. So that's 2.8 with an angle of negative 0.5. We convert that to polar form. So we convert our numerator and denominator to polar form, and then multiply and divide. So J can be written as, so in this case a negative J can be written as 1 with an angle of minus 90. So then we have in the numerator 12.17 with an angle of minus 90 multiplied by our voltage VFS, our Vs, 2.8 with the angle negative 0.5, all divided by 80.9 with an angle of negative 8.65. That simplifies to 0.421 with an angle of negative 186.35. So in the phasor domain, our voltage is equal to 0.421 with an angle of negative 186.35. So in the time domain, that is going to equal to 0.42 times cosine omega t, which is 300, times t minus a 186.35 degrees. Well, notice that our angle theta has exceed 180, and as you know, the angle theta may take on any positive or negative value, but we usually add or subtract multiples of 2 pi, or equivalently multiply multiples of 360, so that the remainder is between negative 180 and 180. Thus, we can convert that to less than r between that interval. So between either 180 and 180, if that's what we want, we could actually add 180, but doing that will end up with a minus cosine based on our trig identities. So the best move to make in this case would be to add 360, which allows us to keep our positive amplitude. So what I'm saying is that if we have a cosine, so cosine of x is equal to minus cosine of x plus or minus 180. So if we add 180 just to take our angle from negative 186.35 to somewhere between our interval, then we'll end up with a negative cosine. So what we can do then is add a angle of 360, and that will solve that problem. So if we add 360, we end up with an amplitude. It's still a positive amplitude of 0.42 times cosine 300 times t with an angle of 173.65 degrees, and that's in volts. So this is VAB of T, the voltage across the capacitor and the inductor. So we can then use node method or node voltage method to find the voltage across our capacitor inductor. So we can do that by, we can call this node B, or in this case just call it V. And what we're doing is applying KCL at that node. So our current I of S is coming in, and another current is going out, and also another current is going out. So we can go ahead and apply our node voltage method. So by doing that, the current I of S is coming into the node A. So we have a minus, and when we use node voltage method, we're basically taking KCL at that node. It's just like a current equation. So minus the phasor counterpart of IS of t. So that is plus A, or in this case V, divided by our impedance for our resistor. We can just use R to represent that, plus V again, all over the total impedance in that branch. So it'll be, we're taking V with reference to ground, so V minus 0 volts divided by the total impedance in that branch. So that is 1 over j omega c plus j omega l, which is equal to 0. So we can then go ahead and move over I. So if we move over our I, and we know that our current is 35 with an angle of 105, and that's in milli. So I could have just probably just run that back and have just 0.035. But in this case, we're just going to include that. And then when we factor out V and combine, when we factor out V, we combine 1 over R plus 1 over the following, and that simplifies to, I'll probably move that a little bit further. That then simplifies to the following, so 0.083 with an angle of 81.35. So we just go ahead, move that over by dividing. So we then end up with 0.422 with an angle of negative 186.35. And that's in volts. So as you can see, our expression here is equal to what we just had here. So based on that, we know by what we've done with our angle from negative 186 to 173, we know that this is going to equal to 0.42 times cosine of 300 times t with an angle of plus 173.65 degrees. So there's a two method. One's a lot simpler, and based on what we did, I would say by finding the voltage at that node, we found the voltage across the two components because those components are in parallel with this. The voltage across the 80 ohms resistor. My bad. So the voltage across the 200 microfarad plus the 15 millihenry is equal to the following, and that should have been, because we normally have to try and, this is going from the phasor domain to the time domain, so this should be written as VAB of t. And as always, we find the voltage across here, thus we know the voltage across these guys. And that's it for today's video. So see you in the next one. Bye.